Hello, am I audible?
Yes, sir.
Okay, that was the last part of thermodynamics, which we have finished. The next chapter is kinetic theory of gas. Okay, Gautam, any doubt from last part?
No, sir.
Okay, so let's start with new chapter, that is kinetic theory of gas. So first, we have to define about property of ideal gas. Property of ideal gas, on the basis of which we have to calculate pressure exerted, thermal kinetic energy due to temperature, and then so on. So first is, in last chapter, thermodynamics, I had defined you basic difference between real gas and ideal gas. So at that time, I defined you real gas is if there is interaction between particle of gas for which there will be some potential energy due to their interaction that are called as real gas. But for ideal gas, there will be no interaction between particles. So first property will be there is no interaction between particle of gas. Each particle will act or behave independently. Next, they will move at same velocity along all different coordinate axes. It means velocity along x-axis, y-axis, and z-axis will be same. They move at same velocity along any coordinate axis. That is, velocity along x-axis, y-axis, and z-axis will be same. So let me define you the vector representation of this. So V vector equals to Vx I cap, Vy j cap, and Vz k cap. Gautam, is it clear?
Yes, sir.
So if you take the magnitude of this particular quantity, so V mod equals to root under x component square, y component square, and z component square. And since these all velocities are equal, so it will be Vx square, Vx square, Vx square, or simply 3 times of Vx square root under. Now this particular quantity, that is mod of this particular representation, is also termed as mean velocity, or if you square both sides, it will be called as square mean velocity equals to 3 times Vx square. So from this part, velocity along any one coordinate will be 1/3 of V bar square. This is called square mean velocity. Next property is these gaseous particle behaves as a rigid sphere, so it collides elastically with neighboring particle or wall of the container. So collision in between them will be always elastic in nature. So they make elastic collision with other particle as well as wall of container. Is it clear? Krishna, any doubt?
No, sir, no doubts.
Okay, just write it down to this. Nabila, done?
Yes, sir.
Okay. Now, using this property, we have to first define pressure exerted by gas. In fluid part, I define you pressure exerted by column of fluid, and that pressure was due to acceleration of liquid or acceleration of fluid. In this part, we have to define pressure exerted due to its motion caused by thermal kinetic energy. So next is pressure exerted by gas on wall of container. Suppose a cubical vessel let's say this is x-axis, y-axis, z-axis. Having dimension of this cubical vessel L, in which we have n number of gaseous particle, each of mass small m. Consider a cubical vessel of side L, in which n gaseous particle, each of mass small m. So suppose there is a particle at this point, which is going along this way, having velocity Vx. So on hitting this wall of container, make it deflected towards this direction. And since this collision is elastic, so there will be no change in its velocity. So velocity will remain same Vx. Gautam, is it clear?
Yes, sir.
So during this collision, first we have to calculate how much there will be change in its linear momentum. So change in linear momentum. Delta P equals to P final minus P initial. For this particle having mass m moving at velocity vx towards positive direction, so final momentum will be mvx in positive direction. Initial momentum is going along negative x-axis, so it will be minus of mvx. So minus minus get plus, so it will become 2 times of mvx as change in linear momentum during this collision. Raza, is it clear?
Yes, sir.
Next, we have to calculate how much time it has taken to go from one end to other end and for this particular collision. So you will say this particle, suppose initially at this particular wall, so it must have traveled along this way L distance and coming back to this L distance. So total distance traveled for this particular collision will be 2L divided by its velocity Vx. So time taken for this collision is equals to distance divided by speed. Distance we have 2L divided by speed along x-axis Vx. Now we have moved change in linear momentum and time taken. In chapter 5th, that is Newton's law of motion, there was a second law which state rate of change of linear momentum is equals to applied external force. Is it clear?
Yes.
So from that part, we can say, so force exerted on wall of container will equals to change in its linear momentum by time taken for that collision. So it will be 2 times of mvx divided by time 2l divided by vx. So 2 and 2 will cancel out. Vx on moving to numerator, it will become mvx squared divided by n. Minashi, in and out?
No, sir.
Okay, just write it down to this. You all have done?
Yes, sir.
So this is force exerted by single particle on wall of that container. So using this, let me define you. Pressure exerted. So pressure is force divided by area of cross section. Force we have m times Vx square divided by L, and area of cross section on which it will strike will be L square. And let's say we have n number of particles. So total pressure will be n times of this. Is it clear?
Yes, sir.
So each particle having mass small m, we have n number of particles. So n times m will be total mass divided by L into L square, L cube times Vx square. So we may write this as total mass divided by total volume, Vx square. This quantity is also termed as density. Vx, we have derived above in terms of square mean velocity as 1/3. Just see this particular expression. Vx square is 1/3 of V bar square. So if you replace Vx square by this term, you will get P equals to mass by volume density 1/3 V bar square. So P is pressure, rho is density, and V bar is square mean velocity of gas in this particular condition. So this will be the total pressure exerted by gas on wall of container. Is it clear? Gautam, any doubt?
No, sir.
Okay, just write it down. Now let me give you a question related to this part. If 10 to the power 20 particle in a vessel strikes at 60° with horizontal on wall of container at 1 kilometer per second. Find change in linear momentum if mass of each particle is 2 into 10 to the power minus 27 kg. Just try to solve using the above concept. Let me give you some hint how to solve. Suppose this is wall of container and normal to it will be this. Let's say there is a particle going along this way at some inclination theta with this horizontal line having momentum m times v. So on reflecting back at same inclination theta, it will have same momentum mv. So break the component of this. So initially momentum along this direction, and on reflection, momentum will be along this way. So for initial part having momentum mv, this and this, it will have two component, mvx cos theta and mv sin theta. On reflecting back mv, it will have component along this direction, mv cos theta and mv sin theta. In y direction, we have same momentum and along same direction. So change in momentum will be 0. So only there will be change in momentum along x-axis that will be responsible for applying pressure on wall of container. So net change in linear momentum in this case will be 2 times of mv into cos theta. And we have how many number of particles? 10 to the power 20. So just multiply it by n.
Sir,
Yes.
why is the horizontal component ignored?
No, I have just neglected vertical component. If you calculate change in vertical component, so delta P equals to P final minus P initial. So final momentum along y-axis is towards downward. So that will be taken as minus of mv sin theta. And minus initial momentum we have again in downward direction. So it will be taken as negative minus of mv sin theta. So this minus and this minus will become plus. So this term and this term get cancelled out.
Okay, sir.
Just put all the values and simplify it. Nabila, any doubt to this part?
No, sir.
Okay. Gautam, just check your calculation. Raza, just check the sign of exponential. Krishna, just check your calculation. Good, Raza. Minashi, just check your calculation. Let me solve. 2 times mass of particle we have 2 into 10 to the power minus 25 kg. Velocity of the hitting is 1 kilometer per second. That will be 10 to the power 3 meter per second. Theta 60 degree cos 60 is 1 by 2 and number of particle 10 to the power 20. So this 2 and this 2 will cancel out. So you're left with 2 into 10 to the power minus 25 plus 3 and plus 20. That will be plus 23. So you're left with just minus kg meter per second. Is it clear?
Yes, sir.
Gautam, any doubt?
No, sir.
Okay. Now next term is thermal kinetic energy, or simply kinetic energy of gaseous particle due to its temperature. As according to the above formula, pressure equals to 1 by 3 rho, we may write rho as mass divided by volume and V squared. So move this 3 and V to left side. So it will become 3 times PV is equals to mv squared. To get kinetic energy, must have expression half mv squared. So just multiply this expression by half and similarly along this part by half. So this quantity now becomes kinetic energy. So it will be equals to 3 by 2 times P into V. Now we may simplify this particular fraction in terms of temperature as kinetic energy is equals to 3 by 2. Yes,
Why did we half it?
since kinetic energy equals to half mv squared, that's why I've divided both sides by half. I multiplied both sides by half.
Okay, sir.
Now, according to ideal gas equation, PV is equals to nRT. So it will be equals to nRT. N is number of moles, which may be written in terms of number of particles as 3 by 2. Number of moles is number of particles divided by Avogadro number times R into T. So move this N to left side. So kinetic energy divided by number of particles equals to 3 by 2 R divided by Na multiplied by T. This particular quantity is also termed as another term Kb, which is equals to R by Na, where Kb is Boltzmann constant, R is universal gas constant, and Na is Avogadro's number. So if you put the value of R, that is 8.314 divided by Avogadro number 6.022 into 10 to the power 23. So you get 1.38 into 10 to the power minus 23 joule per mole per Kelvin. Gautam, is it clear?
Yes, sir.
So we may write this particular quantity, kinetic energy divided by number of particles is also termed as average kinetic energy. So kinetic energy having bar equals to 3 by 2 R by Na is Kb multiplied by T. So this is the average kinetic energy of particle due to temperature. Raza, is it clear?
Yes, sir.
Okay, just write it down.
It's a big N is number of particles, right?
Yeah. You must have learned about number of moles. N equals to given mass by molar mass, number of particles divided by Avogadro number, or given volume divided by 22.4 liter. These different formula to calculate number of moles. Is it clear?
So what is Ke bar?
K bar is kinetic energy divided by number of particles. So it will termed as average kinetic energy.
Okay, sir. So it's a total kinetic energy by number of particles.
Yes?
Total kinetic energy by number of particles.
Yeah.
Okay.
You all have written till this?
Yes, sir.
Now, using this expression, we may define about absolute zero, that is 0 Kelvin. If you put the temperature in this expression to be 0 Kelvin, so kinetic energy or average kinetic energy of particle will become 0. It means there will be no randomness of particle at 0 Kelvin. So we may define absolute zero as the temperature at which there is no randomness in gaseous particle is called absolute zero. Hence, it won't exist at that particular temperature. Is it clear? Just write it down. Have you all done?
Yes, sir.
Okay, let's stop here for today. In next class, I will define you about law of equipartition of energy, then calculation of internal energy, the last part, mean free path of gaseous particle. Then we'll start new chapter, that is simple harmonic motion. Okay?
Okay, sir.
Okay, then we'll continue next class.
Thank you, sir.
Thank you.
Thank you, sir.